Hi everyone, in this video I'm going to talk about what is a buffer solution. So a buffer is any solution that has a weak conjugate acid-base pair. That is a buffer solution. And so what does that mean, a weak conjugate acid-base pair? That means you have a weak acid and its conjugate base. Or you have a weak base and its conjugate acid. So it needs to be a weak acid in its base or a weak base in its con acid. And the only difference between an acid and its conjugate base or a base and its conjugate acid is one hydrogen ion. And what do buffers do? Why are they important? They're important because they resist changes to pH when you add small amounts of acid or base to them. Buffers are how our blood works. If you have a pool, your pool stays at the right pH because of buffers. They're really important. And so let's just look at, okay, the first thing, what would represent a buffer solution? So if I had 1 molar HNO3 and 1 molar NaNO3. Well, the first thing I notice right here is HNO3 is a strong acid. That's nitric acid. And because it's a strong acid, it will not be a buffer. HF and NaF. HF is a weak acid. Now let's look at the second part, NaF. You should know that anything with sodium in it is aqueous, which means that it completely dissolves. So when I say I have 1 molar NaF, that really means I have 1 molar Na ions and F ions. Now sodium is not the conjugate base to HF, but the F minus ions are the conjugate to HF because they're only 1 hydrogen off. And so that would make a buffer solution. Next, chloric acid, HClO3. Well, that's a strong acid, so that will not be a buffer. I don't even need to look at the second part. Next, CH3CO2H. Well, that's acetic acid. It's not on my list of strong acids, so that's a weak acid. So this could be a buffer. And 1 molar NaHCO3. That's sodium bicarbonate. So again, anything with sodium dissociates. So really, that's like I'm saying I have HCO3 ions. Well, these are not buffers because this is not the conjugate base of acetic acid. Those are different substances. So not a buffer. Okay. 1 molar NH3. NH3 is technically a weak base. And NH4Cl. Anything with chlorine is aqueous. So really, that's saying that I have NH4 plus. Well, this is the conjugate acid for NH3, so yeah, that can be a buffer. HCN and NaCN. HCN is a weak acid. NaCN, aka Cn minus, would be its conjugate base, so that can be a buffer. 1 molar CH3NH2 and CH3CO2H. Those are different things. So not going to make a buffer. And then let's look at the last one, NaH2PO4 and Na2HPO4. Again, take out the sodium, because when the sodium is there, it might confuse you. But what we really have is H2PO4, -1, and HPO4, -2. This would be the acid, and that's not a strong acid, that's a weak acid. That would be the conjugate base. So yeah, that could be a buffer. So that's what a buffer is. You need a weak, either acid or base, and its conjugate partner. And if you notice, looking at all of these, they all said you have 1 molarity of each. 1 molarity of base, 1 molarity con acid, 1 molarity acid, 1 molarity con base. So it doesn't have to be a 1 molarity, but they need to be the same amount. A buffer has very close to equal amounts of both acid and con base, or base and con acid. If you don't have equal amounts, it can't act as a buffer. And so let's talk about how does this buffer work? How does it resist pH changes? So let's pretend we have this buffer, hydrofluoric acid and fluorine anions. And so if I added a strong base like NaOH to this buffer, what's going to happen? Well, the base is going to react with the acid. What's the acid? HF. So it would be HF plus OH. And what would that form? Well, the base will neutralize the acid. Whenever you neutralize something, you make water. So it's going to make H2O and fluorine ions. And so I've added in a base, and I make water. And making water does not change the pH. So even though you added a base, it gets neutralized by this acid, no pH change. That's why it's a buffer. And so let's fill this in. Adding OH ions to this buffer will cause the concentration of HF. Now you're going to use some of your acid, so that concentration would go down, and the concentration of fluorine ions would go up because you have made fluorine anions. But again, the pH change, there would be no pH change because you add a base, but it gets neutralized, makes water. Now, what if I added a strong acid like HCl to this solution? What it would do is it's going to react with the base. So HF plus F minus, that's going to make HF. And again, that's not going to change the pH by any significant manner because you've added in an acid, but this conjugate base will neutralize it. Now, again, what's going to happen is the amount of HF will go up because you just made it, and the amount of fluorine ions would go down because those are getting used up. Now, as long as that ratio of acid to conjugate base doesn't change very much, the pH change will really be minimal when you add something to a buffer solution. And that's how buffers work. You can add a little bit of acid and a little bit of base, and the buffer will be able to neutralize it, and the pH will not change. If you add in a ton of acid or a ton of base, then the buffer can't work anymore. So that's buffers. Now, an important formula dealing with buffers is the Henderson-Hasselbalch equation. This allows us to find the pH of a buffer. And so it's pH equals the pKa plus log of A minus, that's the concentration of the conjugate base, over the concentration or the molarity of the weak acid. And this allows you to find the pH of a buffer solution. Okay, so how would we do this? Let's just look at an example. A certain buffer contains 1 molar HCH3COO and 1 molar NaCH3COO. So there's my weak acid, and again, get rid of the Na, so CH3COO minus would be my con base. And it wants us to find the pH of the solution. So reading this, you should recognize I've got an acid con base, that's a buffer. I'm going to use this equation. The first thing is it needs pKa, and we were given Ka. To get pKa, you just do the negative log of the Ka value. So negative log 1.8 times 10 to the negative 5 would be 4.74. There's your pKa. Now that I know pKa, I can plug into this. So pH will equal 4.74 plus the log of my concentration of conjugate base is 1 over my concentration of weak acid is 1. And you get that the pH is 4.74. So this is important to know. If a buffer solution contains equimolar quantities of weak acid and its conjugate base, then the pH of the buffer solution equals the pKa of the weak acid. pH and pKa are equal when you have equal amounts of acid and conjugate base. Let's do another one. Now calculate the pH if you've got 1 molar HC3COO, so that's my weak acid, and I've got 0.8 m of my con base. So this time we have more acid. If you have more acid than base, the pH should be less than pKa because acids lower pH values. Well, let's see if that's true for this buffer. So again, the equation is pH equals pKa, which was 4.74 because this is the same acid as that, plus, and it's the log of the con base, so log of 0.8 over 1. And when you go plug that in, 4.74 plus the log of 0.8, the pH equals 4.64, which matches what we had thought. More acid drops the pH. Okay, let's look at the next example. Calculate the pH if you have 0.8 M weak acid and 1 M con base. So now in this example, we have more base. Having more base should make the pH go up. And let's just check and confirm that it does. So pH equals pKa, 4.74, plus the log of, remember it's con base over acid, so 1 over 0.8. And plug that in. You get the pH is 4.84. So that is a buffer solution. Again, it's a combination of acid and conjugate base. They work to minimize changes to pH when you add in an acid and a base. Your best buffer has very equal amounts of acid and con base. And I hope this video was helpful.